Hello everyone, this is a lecture demo and we're going to talk about, I'm going to talk about, since I'm the only one here, ICMP, the ICMP protocol, which within the TCPIP stack. So we're going to look at what ICMP is, why do we need it, and how it works. So hopefully you've seen this before, but this is the TCPIP stack on the left-hand side and what operates there on the right-hand side. And of course we have our application up here, so our real app, and then that will talk to the application layer of the TCPIP stack, which will then talk to the transport layer, and then the transport will talk to the internet to the data link, and then the data link will talk to the physical and send it out on the wire. And then when the packet comes back in, the physical will talk to the data link, and then data link will talk to internet to transport, transport to application, and then finally the data that's received will be sent to our application running on our system. So we're looking at this level here at the internet layer, and this is where ICMP lives. This is where ICMP operates. So what is ICMP? ICMP is a transparent protocol, but without it, networks wouldn't, well, networking hardware couldn't work. So it's used by device nodes and routers to communicate network level information. So things like error reporting with unreachable host, unreachable network, port problems, protocol errors, things like that are reported through ICMP because they really have the other layers have no interest in them. So if I'm not sending anything, then the transport is useless, and if I can't get anything, then the application is also useless. Excuse me. So ICMP is carried in IP datagrams, and it's described in RFC 792 and updates to the RFC. So it's, as you can see, it's quite low. It's quite an old protocol. It's been around for a while, and it's very it's part of the fundamental operation of the internet. So ICMP messages are very, very simple. So what the message contains, so the message body, so the headers are there, some of the header information is there, and then we have the type, and then the code. So we differentiate, there are these types and codes to differentiate the type, and then the first 8 bytes of the datagram causing the error. So as you can see here, we have echo reply, which is 00, and echo request, which is 80. That is what ping uses, and the rest are error messages or information about something that's going on. So these two are error messages, these are routing. But this is all of the ICMP messages. So, ping and ICMPs. The ping command is something that we use to directly use ICMP. So that will directly use ICMP. So it's used to test communication between nodes. So there are several options to the ping command, and they're slightly different depending on where you run it and what version. So if you run it on Ubuntu, you'll see something like this. So what I've done is I've said ping Cora. So it'll look up the IP address for Cora, that's in the background in the DNS, and it gets the IP address. And the ping on Ubuntu sends 56 bytes of data. And then the way ping works on Unix systems is it just pings forever until you kill the process. So this is what we're seeing here. Here's where I killed the process. So ping on most Unix boxes will look up the IP address, send 56 bytes of data in the packet, and expect a response. So what ping is doing, it sends an echo request, and then whatever device we're pinging sends an echo reply. So let's take a look at some live pinging. So first we're going to ping using a Ubuntu VM at Dawson. So what that means is the VM is on the same network as most of my other systems. So if I ping Sonic, for example, it looks up the IP address for Sonic, sends 56 bytes. And notice we see there, so this is the first packet that's sent, second, third, fourth, and fifth, and the time to live, which I will be talking about soon. And it gets a 64-byte response. And notice the time that it took is 0.341 milliseconds, 0.272, 0.4. So it'll give you the average. Oh no, it actually doesn't give that. But here, oh yeah, minimum, average, maximum, and I can't remember what MDEV is. Give me a second. Okay. Okay, so MDev is the deviation. So what that means is there a lot of variance in the times? So that's relatively low. So there's not a super lot of variance. Most of them are around 300, as we can see here. So that's what ping will look like on most Unix boxes. Let's try it on a Windows box. Let me just pull this out. Pull in my command prompt. Let's clear this. Doesn't really matter. So let me ping Sonic from here. So you notice this is the ping. So the way ping works on Windows is it sends, it looks like 4 packets. That's just the default, and we can change these things. So there are options for ping for Windows, options for ping for Unix. But what we have here is it sent 4 packets, and it gives us the statistics. It says, so 0 loss is good, and it says the minimum is 12 milliseconds, maximum 14, and the average is 13. So it doesn't give us standard deviation between them. But notice it's 12 milliseconds, which is considerably more than 0.341 milliseconds. So why do you think that might be? What do you think? Why is the time so much shorter here? Well, it has to do with where the VM is. The VM is relatively close to, maybe not on the same exact LAN, but they're on connected LANs. Whereas my computer at home has to go through an internet service provider and then onto the LAN for Dawson. So it's much further away. So you would expect this to be different. So just a little word about a denial of service attack that can be done with ping flood, flood, or sometimes called ping flood of death. So the TCPIP stack on most installations which is part of the kernel, of course, is by default configured to respond to an ICMP echo request with an echo response. So the ping sends an echo request, the device responds with an echo response or reply. Because it has to respond, if it gets a lot of echo requests in a short period of time, then it might have to use all of its resources in responding. So if you think of like a tennis, you've got a tennis racket, and there's a tennis ball machine lobbing tennis balls at you. Well, if they're within a period of time, then you can send them back no problem, and you don't get exhausted. But what if it ramps up and you've got thousands of them coming in fast? Well, then you're probably going to drop to the floor. So that's the same way with same thing with ping. So some devices change the configuration to not respond to echo requests, but this blocks legitimate ping use. So you don't always want to do this. So it is possible to do it, but you don't always want to do it. And you can block fractions, so you don't block legitimate ping, but this gets a little more complex than we want to get right now. So the other thing that we can use traceroute with, so this is use ICMP with, is traceroute. So routers will use all of these things, but I'm talking about the two things, ping and traceroute, where we'll use it directly. So it's kind of a special use of ICMP error responses. So the source sends a series of UDP segments with a weird port number, and the first set of 3 has a TTL of 1, the second set a TTL of 2, the third of a TTL of 3, and TTL is the number of routers maximum that it can pass through before it's discarded. So this is the way the IP works, the IP layer works. The TTL is, I can go through, if my TTL is 100, then I can go through 100 routers before we can't find it. So we start with 1, 2, 3, and so on, and we go up. So what happens is the first one reaches the first router, second will reach the second router, and so on. When they each reach a router, the router drops the datagram and sends back a message saying, okay, TTL expired. When it reaches the final destination, the device sends back a message type 3, port unreachable, because we've used this weird port. So when traceroute receives a TTL expires, it knows that's one of the hops along the way. And when it receives port unreachable, it knows that we've reached the end. So it looks like this. So TTL1 to the first one, and it will send back an ICMP repeated. And then the packets with TTL2 will go here, and then they'll get TTL exceeded. And then the packets with 3 will go here, and here, and here, and they'll get exceeded. And then finally, the ones with 4 will reach the destination, and you'll get destination unreachable. And that's how we build the traceroute. So these are two examples of trace routes, and the 8844 is the DNS, the Google Open DNS 8888 and 8844. So as you can see here, the first hop is always my gateway. And this is a website, Nouveau Palais, which is in Montreal, but I'm not sure exactly where it is. And you notice here we go through some of the same hopping off points. So this is our gateway, and then this is getting off of Dawson, and we'll look these up at a later point. So these three are all the same. So sorry, 1, 2, 3, 4 are the same, and then we start to deviate a little bit. But as you can see here, this one timed out without responding, but the others give you the response time for each of them. And note, the farther away they get, the bigger the response time. Sorry, it keeps obscuring it because of that stupid thing. So number 15 for Nouveau Palais is 21 milliseconds for response for each of those. It's also the Google has a lot of resources, so you can't. It's not just distance. It's response time also has to do with it has to do with proximity and resources. So. So on the left, we have one that's considerably farther away from us than this one is, but possibly. But as you can see, it collects. So the first one here, this would be TTL1 responding to it, TTL2, and then all the way down to 10, which is the port is unknown. Same thing here. TTL1, 2, 3, 4, they'll respond with the expiry, and then all the way down to 15, which will respond with port destination unknown. So ICMP is a protocol that's used transparently by routers and in error detection, but we can use it to detect network errors and figure out what's going out along the way to our destinations. Thank you.